There. Can you hear me? Okay. So, you know, there's an exam coming up next week. And to prepare for the exam, go to the folder on the Lon Kappa site called Hints and Messages. It's this folder. And it's got a bunch of things in there, hints for different homework assignments and so on. But for the exam, the second midterm exam, you want to look at these three files. There's one called Review Number 2. That'll review all the material that's on the exam. There's Practice Exam Number 2. That's what we're going to look at today. These are some exam questions. These questions have been on exams in the past. They won't be on the exam this year, but anyway, practice doing these problems. Do these problems. And that'll give you practice because the problems on the exam will be on similar topics. They won't be the same problems, but they'll be the same topics. And then there's a third file called Solution Number 2 that gives you the answers to the exam questions. So do the practice exam and then check your answers. Now, what we're going to do today is we're going to look at the practice exam. All right, so oops. All right, so to prepare for the midterm exam, you need an equation sheet that you can refer to during the exam. You're allowed to have an equation sheet where you have the equations written down that you'll need to use during the exam. A good source of those equations that you can put on the equation sheet is the exam study guide, which you'll find at the end of each chapter. So at the end of each chapter, there's a one or half a page guide to equations from that chapter. And that's a good source of the equations that you're going to need. Also study Review Number 2. That also has the equations that you'll need. So make that equation sheet. And now let's take a look at some of these problems. So here's the first question. A duck flying overhead due north in a magnetic field. It has an electric charge. What's the magnetic force acting on the duck? Never mind that it says it's a duck. Just think of it as a particle moving north with some velocity v. There's a vertical magnetic field pointing down towards the Earth. That's the Earth's magnetic field. Here's the east-west directions, if this is north. Now, the first question is, what's the magnitude of the magnetic force? There are actually two parts. The second part will be, what's the direction? So the crucial thing is the force. So you need to know the equation. So on your equation sheet, you should have the equation. Force is Q V cross B. That's the Lorentz force, the magnetic force on a moving object. Charge Q, velocity V, and magnetic field B. Now, in this problem, V and B are perpendicular. So the cross product will just be V times B in magnitude. So the magnitude is just QVB. Just multiply these three numbers together. Part two is to determine the direction. Well, that involves a cross product. So you have to apply the right-hand rule. If your fingers curl in the direction from V to B, then your thumb points in the direction of V cross B. And if Q is positive, that's the direction of the force. So that's how you use the equation from the equation sheet to do the problem. Now, here's question number 2. 2 circular conducting wires are in the XY plane. They're carrying currents. So this has a current going this way, I1. This has a current going this way, I2. Calculate the magnetic field at the center of the 2 loops at this point. Now again, you'll need to know the magnetic field at the center of a circular loop of wire. And that's something that you should have on your equation sheet. It's mu naught I over 2r. R is the radius. N hat is the direction. It's perpendicular to the plane of the circle. And again, you'll find that that equation is in the exam study guide for chapter 28. So if you've written it down after looking at chapter 28, you'll have it available. Of course, here we have 2 loops. So we have to use the superposition principle. We just add them. By the right-hand rule, the magnetic field will point perpendicular to the XY plane. N hat is perpendicular to I, the current, the circle. So we'll have B1 in the Z direction and B2 in the Z direction. We'll add those. We'll take the magnitude, the absolute value, to get the magnitude. The currents are in the opposite direction. So one will have a field in the plus Z direction. The other will have a field in the minus Z direction. The part 2 of the problem is to calculate the direction. And again, there's a right-hand rule for that, which is explained in the study guide for chapter 28. If the fingers of your right hand curl in the direction of the current, then your thumb points in the direction of the magnetic field. It's not the same right-hand rule as we have over here for the force, but anyway, this is explained in the study guide. So that's the second question. Here's the third question. A regular hexagon wire loop, a regular hexagon-shaped wire loop, side lengths are A, that's given, carries an electric current I, which is given. And the question is, what's the magnetic field at the point P? Now, this problem is actually quite hard because you need to know the magnetic field on a finite wire segment. You'll certainly have on your equation sheet the magnetic field on an infinite wire, but this is only the segments of this hexagon are only finite. And that's a more complicated formula. Actually, the only way I was able to figure this out was to use the Biot-Savart law and do the integral. And there's a formula after you do the integral, which is in terms of A, the size of the side, let's take this side, and R, which is the perpendicular distance. Now, you probably won't have that equation on your equation sheet. However, if you look at the review number 2, you'll find that there's an equation there for the magnetic field for a finite wire segment. Now, of course, in this case, there are 6 wire segments, and they each make the same contribution by the right-hand rule. So the magnetic field at P will just be 6 times the magnetic field from one side. And as I say, look in review number 2 to find this equation. But try to do this problem for the numbers that are given and check your answer. The numbers are given in the practice exam number 2 on the Lon Kappa site. So that's a problem where you are given a current and you have to calculate a magnetic field. Here's question number 4. A steel beam is accidentally dropped from a construction crane from a certain height. It's moving in the Earth's magnetic field. What's the induced EMF just before it hits the Earth? Never mind that it says it's a steel beam. This isn't a very realistic idea that it's a steel beam, but the idea is you have a conducting rod moving in a magnetic field. Now, the Earth's magnetic field, let's say the horizontal component is back this way. So you have a conducting rod passing through a magnetic field. Well, there's an electromotive force because of electromagnetic induction. There's a change in flux. This is called motional EMF. So you'll immediately recognize that this is an example of motional EMF. It's shown in figure 29.13. Chapter 29 in the book is all about electromagnetic induction, and one of the topics is motional EMF. And figure 29.13 is exactly this problem. And there, the authors give derivation of the equation. The potential difference is the velocity times the length. So this is length times the magnetic field. This would be the perpendicular component of the magnetic field. So that would be the horizontal component of the Earth's magnetic field. So, you just have to multiply these 3 numbers together. Being careful to take into account micro Tesla means 10 to the minus 6 Tesla. Now, you're not given the velocity. So what are you going to use for the velocity? Well, this object is falling down to the ground, and it's just falling in Earth's gravity. So you have to think back to an equation from physics 183, equation for free fall. This is one of the equations for free fall. There are several equations for free fall. This one relates velocity and distance. So as it's falling down here along the y direction, the change in v squared is 2 times the acceleration due to gravity times the distance, delta y. That would be the height here, the 9.49. So again, go to a quiet room, do this problem. Do this problem and check your answer. Check your answer against the solutions number 2. So this is an example where you have motional EMF. We have motion of a conductor through a magnetic field. That's one source of electromagnetic induction. That's one example of electromagnetic induction. All right. Here's problem number 5. In the figure, a region with constant magnetic field is shown. Now, X's mean the magnetic field points away from you. So to indicate it's hard to draw in 3 dimensions. To indicate a vector pointing away from you, there'll be an X. So you're looking at the back of the vector. You're looking at the feathers on the back of the arrow. So that's the meaning of these X's. An arrow pointing out towards you will be drawn as a dot. or possibly a dot surrounded by a circle. That indicates a vector pointing toward you. You're looking at the point of the arrow. Here you're looking at the feathers of the arrow. Now there's a wire loop that's moving into the magnetic field. So immediately you see that, you know there's changing magnetic flux. So that's, again, going to be electromagnetic induction. So this is obviously a problem which is going to involve electromagnetic induction. There are two questions. Now, how would you calculate the electromotive force around the wire loop? Well, Faraday's law says the electromotive force is minus ddt of the flux. And the flux is the magnetic field times the area. Now, the magnetic field is not changing, but the area passing through the loop is changing as the loop goes into the magnetic field. So you would have the derivative of the area. The area is the length times the width. The length is changing. The length of the, if this has come in part way, then the length would mean this length would be L. And this distance would be W. So W isn't changing, but dl dt is exactly the velocity of the whole loop. Now, actually, in this problem, I don't think you're asked to calculate the value of the EMF, but this is the equation that you would use to calculate the value of the EMF. The strength, or the strength of the voltage. If you're asked to calculate the current, you would have to know the resistance of the loop. Faraday's law tells you the voltage divided by the resistance would be the current. But in this problem, the two parts just ask you the two directions. What's the direction of the electromotive force? Is it clockwise or is it counterclockwise? Well, for that, you need to know the right-hand rule for electromagnetic induction. If the magnetic flux away from you is increasing, then the induced EMF opposes the change of the magnetic field, so it would be pointing out towards you. So it would be in the direction corresponding to pointing out towards you, which is to say, what's that? Counterclockwise. And then the other part is to calculate the direction of the force. Here we have a wire going through a magnetic field with a current. Current will be the EMF divided by the resistance. There'll be a force. The force on a wire with current I, and the vector is in the L direction. Is, in this case, I don't know if this is clockwise. If this is counterclockwise, let's see. If this is counterclockwise, then here the current would be upward. Then L cross B would be, I guess, well, you'd have to figure it out. So you have to use the cross product. So again, you have to use the right-hand rule to determine the force. So you see how you have to have this equation in mind. And so it should be written on your equation sheet. And this equation. So that's the kind of equation you would want on your equation sheet. You're not actually using the equations here. You're just using the directions. So when you read review number 2, make sure you study carefully the directions, which are given in review number 2, which usually involve the right-hand rule. Question number 6. 7.5 volt battery is connected in series with a resistor and an inductor. Okay, so you see right away, This is an RL circuit. There's a resistance and there's an inductance. And it's a DC circuit because it doesn't have any alternating current generator. It just has a battery. Battery can only produce direct current. So it's a DC circuit with resistance and inductance. There's a whole section of that in the book. It has a time constant tau, which is given, and it has some maximum current. What's the value of L? Well, you're going to have some equations about the RL circuit on your equation sheet. So again, you can get that from the exam study guide. That would be, I guess, in chapter, I don't know, chapter 29. Maybe you remember from one of the homework problems, you had problems like this on the homework. Maybe you remember the time constant for an RL circuit is R over L. Or is it L over R? Which one is it? Is it R over L or is it L over R? Well, if you've got the equation on your study, on your exam, on your equation sheet, and you'll find it in the exam study guide for chapter 29, or you'd also find it in the review number 2, you would have written down whether it's R over L over L over R. Otherwise, you have to figure out, is it R over L? Is it L over R? What you remember is that the voltage across an inductor is L di dt. That's the voltage difference between the ends of an inductor. And for a resistor, it's Ri. So these have to have the same units. So the units here have to be the same. Now current and current have the same units. So L over time has to be R. L divided by time has to be R. So evidently, just by dimensional analysis, just by analyzing the dimensions, time must be L over R. So you could figure it out if you didn't have it written down on your equation sheet, but better to find the important equations from the exam study guide. Okay. Question 7 is an RLC series with an AC generator. So we have an RLC circuit where these are connected in series. And there's an alternating current source of electromotive force. So again, you'll remember that from the chapter on AC circuits. Make sure you have some of the important equations on your equation sheet. You need the equations for a series RLC circuit. Now, what are you supposed to calculate here? Well, the first part is to calculate the impedance, which is going to be in ohms. There's also a part 2. Now, impedance, which is always denoted by Z, which has units of ohms, it's the square root of R squared plus XL minus XE squared, where R is the resistance, so that's this R. XL is the effective resistance. It's actually called the impedance, I guess, of an inductor. And XC is the effective resistance of a capacitor. An inductor, a capacitor have a kind of something equivalent to resistance that depends on the frequency. So that's the formula for impedance, but that doesn't do you enough good because you don't know what XL is and XC. So you better know what X sub L is. And you better know what X sub C is. But again, if you look on the equation, if you look in the equations in the review number 2 or in the exam study guide, you'll find formulas. XL is 1 over omega L. XC is omega C. Those will be given in terms of omega. So these depend on omega. Now, what's omega? Well, omega is not given in the problem. What's given is F. So F is called the frequency. Omega is called the angular frequency. So you need to know what angular frequency is. It's 2 pi times F. Now, maybe this is just something you remember. Maybe you don't need to write this down on your equation sheet. You know, frequency has units 1 over seconds or hertz. Angular frequency has units of radians per second. The 2 pi is the number of radians for 1 complete cycle. So omega is 2 pi F, or F is omega divided by 2 pi. But anyway, you know, if you're going to write down the equations for impedance, they'll depend on omega, and you have to know what omega is, because omega is not given in the statement of the problem. Now, part 2 of the problem says, what's the power factor? And I don't have that written down here to talk about today, but you'll remember power is delivered by the source of EMF, the generator. And there's a formula for power, which also depends on impedance. It depends on resistance and so on. It depends on the phase angle, I think. So there's a so-called power factor, which is something related to the phase angle. I don't have it written down here, but again, read the review number 2 and study the exam study guides. And make sure you have that, because I don't know what's on the exam. I don't know what problems are going to be asked on the exam, but I would be surprised if there's not a question about the RLC circuit. All right, here's question number 8. You're building a power supply in your garage for an electronic instrument. You purchase a transformer for the project. Primary coil has 150 turns, secondary coil 120 turns. What voltage is supplied by a secondary coil if the primary coil is plugged into a wall socket? You know, these problems sometimes have a lot of kind of red herrings. Not exactly red herrings, but just a lot of extra stuff that you don't really need to use. This is just a question about a transformer. So the way I would approach a question like this when I was a student was, I would start by just writing down the information that's given in the problem. Well, let's see what's given. Well, N1 is 850. N2 is 120. This is a step-down transformer. The frequency is 60 hertz. That's F. Omega is 2 pi times the frequency. I'm not sure I'll need that, but the voltage for the primary side, so that's V1, is 120 volts. I guess that's the RMS voltage. Okay, so that's the information I have. Now I need to know what's the transformer equation. What am I trying to calculate? What's the voltage supplied by the secondary coil? Well, that's obviously V2. I know N1, N2, and V1. I got to know V2. Well, I'll have that on the equation sheet. So again, this would have been in chapter 30, the chapter on AC circuits. Transformers are often found in AC circuits. They transform the voltage. What does a transformer transform? It transforms the voltage. It doesn't transform the frequency. So the frequency is sort of a red herring. Well, that's part one of the problem. Now there's part two. And part two asks about the currents. Something about the currents. I don't have the equation written down here, but if you look on the practice exam, you'll find out what the question is about currents. So, or the currents, well, you know, there's I1 and there's I2. They're two currents because they're two coils of wire. So, you know, you're going to need some equation which relates the information that you're given and I1 and I2. So again, sit down in a quiet room and do this problem. Work out the number. Use the numbers that are given on the practice exam and calculate the number. And then check your answer. What else do we have? We have electromagnetic waves. This past 3 weeks, I guess it is, included electromagnetic waves. So you'll certainly have some questions about electromagnetic waves. You just finished the homework assignments, the Lawn Kappa homework problems about electromagnetic waves, and you saw that there were many things to know about electromagnetic waves. So you can sort of expect to have a problem about electromagnetic waves. In this problem, they tell you that the electric field is oscillating in the z direction. And it has formed some amplitude, sine kx minus omega t, where the value of omega is given. And the first question is, what's the frequency? Now, when they say frequency, what they mean is F. That's the 1 over the period of oscillation. As the wave goes by you, here's the wave, and it's traveling in some direction. Well, you can see it's traveling in the x direction. So it's going in the x direction. It's oscillating in the z direction. So that would be the z direction. No. Yeah, it's oscillating in the z direction. It's traveling in the x direction. If you're just sitting at what, you're just standing at one point as the wave goes by you, you'll see an oscillation of the electric field. And the frequency is 1 over the period of that oscillation. Well, that depends on this parameter, which is not the frequency. That's the angular frequency. So you need to know the equations for electromagnetic waves. The electric field is some amplitude times sine kx minus omega t. Now, what's the wavelength? Well, the wavelength is 2 pi over k. And what's the period? Well, the period is 2 pi over omega. So the frequency is omega over 2 pi. You know, the sine oscillates whenever the argument changes by 2 pi. So omega times 1 period would be 2 pi, and k times 1 wavelength would be 2 pi. So that tells you how to calculate period in terms of omega and wavelength in terms of k. Also, you need to know that the speed of the wave is the wavelength times the frequency. Now, this equation would solve the first question, but there are actually 4 questions. I mean, it's one question, 9, but there are 4 parts. So it might ask, what's the magnetic field? Well, there you have to remember, put in a different color, the magnetic field oscillates, I don't know if I'll be able to draw this, but the magnetic field oscillates perpendicular to the electric field. The magnetic field, the electric field, and the direction of motion are all perpendicular to each other. It's an orthogonal triad. So if the electric field is oscillating in the z direction and the wave is moving in the x direction, then the magnetic field must be oscillating in the third direction, the y direction. And it'll be some amplitude beta times the same sine kx minus omega t. What's beta? Well, again, a property of electromagnetic waves, and you should have a collection of equations about the electromagnetic wave. E is equal to c times b, where c is the speed of light. Now, the equation sheet may tell you the value of c. It doesn't tell you here. There is a front page for the exam which gives you some physical constants. But oddly enough, on the practice exam, that didn't include the speed of light. So to do this problem, you'd have to know the speed of light. So maybe you better write that down or just remember it. It's approximately 300 million meters per second, or 3 times 10 to the 8th meters per second, or a little more accurately, 2.998 times 10 to the 8 meters per second. There's also a relation between that speed and the magnetic and electric force constants, mu0 and epsilon0. Now, actually, the values of mu0 and epsilon0 are given at the front page of the practice exam. So maybe if you didn't remember the value of c, you'd have to calculate this 1 over the square root of mu0 epsilon0. If one of the 4 questions had to do with speed. You know, one of the 4 questions might be, what's the wavelength? Well, the wavelength is 2 pi over k. K is not given. So that doesn't help you. But remember, wavelength times frequency is the speed. And the first question was, what's the frequency? So you already calculated the frequency. The wavelength would just be the speed over f, but you have to know the speed. So what's the speed of an electromagnetic wave? Well, you know, if you look up in the table of fundamental constants in the front of the book, it's 2.998 times 10 to the 8 meters per second. Maybe you should have that written down. Or you could calculate it from this if these constants are given. All right, so there's a lot to say about electromagnetic waves. And you've done a lot of calculations on the most recent homework assignment, so you should remember some of those, but if you forget the exact formula, that's why you need the equation sheet. Here's another one involving electromagnetic waves. You have a radio transmitter, that is to say an antenna, which emits electromagnetic waves with a single wavelength. The amplitude, no. The maximum electric field is 738 millivolts per meter. So that's the amplitude. But of course, it depends on how far away you are from the antenna. So that's at a distance 5.17 kilometers. So again, start by writing down the information that you have. And then what you're trying to calculate, let's go back to green. What you're trying to calculate is the amplitude of the magnetic field. All right, so let's start by writing down the information that we're given. Well, the maximum electric field is 0.738 volts per meter, 738 millivolts per meter. That's at a distance of 5,170 meters. Because, of course, an antenna produces an electromagnetic wave, which is spreading out. And as you go to farther distances from the antenna, the strength of the electric field decreases. In other words, the energy spreads out as you go farther away from the antenna. So here's the antenna. And so we're considering a particular point here at a distance 5,170 meters. All right, well, again, one of the important equations about electromagnetic waves is the relation between the electric field and the magnetic field. E is C times B, where C is the speed of light in vacuum. That 2.998 times 10 to the 8 meters per second. And that's what you're trying to calculate. B, the maximum magnetic field. So the maximum electric field would be C times the maximum magnetic field. So E max is given, C you know, so you can immediately calculate B max. So that you can do in just have to plug the numbers into your calculator. So you can do that in probably 30 seconds. But that's only part one. Then there's part two. Part two says, what's the power of this antenna? So, suppose this is, WKAR. They have their radio antenna here. And it's producing radio waves spreading out from that antenna. And you go out to a distance here, R, which is given. What's the total power being produced by WKAR? Well, maybe you remember the power spreads out over a circular wave. That's why it says it's a point source. It's a point source, so you have circular waves going out. And so the power is proportional to 1 over R squared. No. That's not the power of the antenna. That's the energy flux, pointing vector. The pointing vector is proportional to 1 over R squared. And the power is the total energy. This is the energy per unit area. So the total area of a sphere is 4 pi R squared. So you have to multiply the energy flux by 4 pi R squared. That'll give you the total power going out through that radius. So to multiply by that. So, you'll have the equation if you make your equation sheet that the power, that the energy flux is the power over 4 pi R squared. Now, is the power given? No, the power isn't given. What's given is the electric field. What you're looking for is the magnetic field. Well, no, you already calculated the magnetic field. Let me see. So now you want to calculate the power. So the power will be the power flux times 4 pi r squared. But how does that determine B max? Well, here you have to know the relation between the Poynting vector it's E times B divided by mu zero. So I guess you don't need this. Well, yeah, you do need this because you have to multiply by 4 pi r squared to get the total power in the antenna. But you already know E, that's given. You already know B, that was part A of the problem. Mu zero is just a universal constant. That'll probably be written down on the front page of the exam. This gives you the maximum, you know, if you put in here E max and B max, that'll give you the maximum energy flux. You probably want the average energy flux. You probably want to say the power is 4 pi r squared times the average energy flux. When you take the time average, you know, E oscillates as sine omega t. B oscillates as sine omega t. The product goes like sine squared of omega t. Sine varies between -1 and 1. Sine squared varies between 0 and 1. The average of sine squared will be a half. So you probably want S is E max, B max over 2 mu zero to get the average of the Poynting vector. So, you know, there are some things to think about in doing this calculation. And let me just say, go in a quiet room and do this problem. And then check your answer with the solution to make sure that you're understanding correctly when you use the maximum field and when you use the root mean square field, the average field. Finally, I think there's one more problem. Oh yeah, I think some of the constants like mu zero and epsilon zero, you'll probably be given on the exam, so you don't have to write them all down. Now there was one more problem. Have I still got it? I thought there was one more problem. That's question 10. I thought there was also a question 11. Yeah, here's question 11. It has to do with the polarization of light. So unpolarized light passes through two polaroid sheets. The first polaroid sheet is vertical. The second sheet is at some angle, 27 degrees to the vertical. What fraction of the initial light is transmitted? So you have some intensity here, but this is not polarized. And now you have some intensity here, which is polarized light. You actually have three polarizations. You have the incident polarization, intensity. You have the intensity on one side of the first polarizer, so you can call that I2. And then you have the intensity on the other past the other polarizer. You call that I3. What you're trying to calculate is the fraction of initial light is transmitted. That means, I think, the fraction in terms of intensity. So I think what you're looking for is I3 divided by I1 would be the fraction. So I don't have anything to say about this. Section 31.6 in chapter 31, the chapter on electromagnetic waves, there's a section on polarization. I think there was a problem pretty much the same as this on the last homework assignment. To make sure that you're getting this, do this problem and check the answer. Now that it's taken a little less than an hour, but I think that pretty much goes over all the questions on the practice exam. The actual questions on the exam will be different, but they won't be using a lot of different equations. So if you make sure you have those equations well in mind when you come to take the the timed exam, you should be able to find the equations that you need for those calculations. Any questions? I didn't really plan to say anything more than this. I'm recording this, so if somebody asks you about the recording of the equation of the Zoom meeting about the practice exam, tell them to go to the YouTube channel, and I'll put the recording there. So good luck on the exam. I want to stop recording.